right, on this problem, we're going to be using something known as the washer method in order to find the volume of a solid. And the reason for that will be apparent. We won't be able to use the disk method on this one, so you'll see why in just a moment. But we're going to find the volume obtained by revolving the region between y equals x squared plus 4 and y equals 2 about the x-axis for x values between 1 and 3. So let me kind of get a general graph of what we have here. Now we have x squared plus 4. So, if we had an x squared function, this would just be translated up 4 units. So it's going to look like an x squared function. It's just going to be up 4 units. And I'm going to do a really gentle curve with my x squared function. And then we also have the line y equals 2. And so that just means that we're going to have a line at 2. Okay? And then we're talking about the region from 1, slide this in, from 1 to 3. So we would get the area of this region right here. Okay, and then we're going to rotate it around the axis. And so I'm going to use a Wolfram demonstration just to kind of get the idea of what this thing is going to look like, and then I'll draw it. Now this is not an exact, it's not the exact same thing as this problem we have right here, but it'll be pretty close. So we kind of have the same idea here. We have the area between two curves, and we're going to rotate it. So this is the idea. We're going to swing it around the x-axis. And so when we do that, what's going to happen is we're actually going to create this solid, okay, or a solid similar to this one. Okay, so that area is going to go around, and it's going to create a solid, and you can kind of see, how it's going to look in the middle. And then let me rotate this. And so you'll notice that this is going to kind of be like a donut in some sense. There's going to be a hole through the middle of this thing, right? And so what we're looking for here is the volume of the solid that's created, but this one's going to have a hole in the middle of it, right? And so the way that we're going to be able to calculate this, if you remember the disk method, the disk method says that we want pi times the integral from a to b of the radius squared times the height, and this just means that we're taking all of the heights from a to b. And so this is pretty much just the volume formula of a disk. But now we can't use a disk, because if you remember when I said we use the disk method is when our area that we're rotating around the axis is actually right up next to the axis of rotation. And so you can see that we have this gap in between our area and our axis of rotation. And so that gap is what's going to actually create, the hole like what we had here. So, when you look in the middle of this thing, the gap between the area and the axis of rotation is going to create a hole in the middle. And so what we're going to have to use is the washer method. And if you just think about it, if you know what a washer is, it's kind of like a something that you use in building, but it's like a shape, that has a hole in the middle of it. And so instead of using a disc, we're going to have to use a washer, this shape with a hole in the middle of it. But I think this is actually easier if you just think about it like two volumes, okay? In the same way you would with an area, if you had a graph and you had, some large area and then you had some lesser area, okay, like with the area between two curves, if we were looking for the space in between these two curves right here, then we could just take the large area, right, all of this green space, and then we could subtract out the area of this little red space right here. And so, the larger area, that is the green, minus the smaller area, the red, would leave us with the blue. Well, you can think about it the exact same way with a volume, right? If we were to rotate both of these things around the axis, and so let me just say we're going to rotate this, and we would get a shape, maybe something like that. Let's see where we go here. All right, and then there's this other shape that we would rotate as well. So this one's going to be going through here. what you kind of come up with, you could come up with is two separate volumes. And we could use these two separate volumes because in the end, we could do the exact same thing that we would do with, excuse me, with an area, right? If we take the volume of the large shape, that's kind of the red one that I have drawn up here right now, and then we subtract out the volume of the blue, the blue volume is just kind of this tunnel almost in between here, right? And so if we took the whole red shape and then subtracted out that tunnel in the middle, then what we could come up with is the volume that's left over. So the idea here is that we want to take the big volume and subtract out the smaller volume, okay? So if we use the disk method to set up a volume for this red shape, the larger one, then we would be doing pi, just using our disk method here. And I'm going to set one up for the larger function here. So it would be pi times the integral, and remember we're going from 1 to 3, so from 1 to 3 of the radius squared. And on the larger function, the big one, going from the x-axis to the red line would be our radius, okay? And so the radius for that one is the function, it's just the height. The function will give you how far it is from the x-axis to the red line. And so remember, we just want to use all of those heights. Okay, so our radius every single time will just be our x squared plus 4 function. That is going to be equal to our radius. Well, the formula says radius squared, so we have our radius in here, and now I'm going to square it, dx. So this right here would be the area of the large volume. But then we need to subtract away the area of the smaller volume, so the smaller piece. So it's going to be pi times, and I'm just using the disk method again, so the big volume minus the small volume, and we're going to go from 1 to 3. Our function now is just y equals 2. So my radius is equal to my function, so it's just going to be 2 squared with respect to x. Right? All of these disks, from the x to the line, from the x to the line, all of these disks are going to have a radius of 2 because that's my function. Now, if I take these two things right here, and let me see if I can get all of this down here so I can mess with it a little bit. Right? I'm going to take all of these. From 1 to 3. This. Erase this. Okay. So, now that I have this thing set up this way, let me bring all of this. All right, and then I don't want that. Okay, I can kind of start using some properties of integrals here in order to, simplify this. If you notice, our integrals are both going from 1 to 3 with each of these, and each of them are being multiplied by pi. So what I'm going to do is basically, you can think of it almost like factoring out a pi times the integral from 1 to 3. So this, new thing would be that pi times the integral from 1 to 3. And so our properties of integrals say that, if we have a function g of x minus a function f of x, and they're both going from the same points, from a to b, and in this case from 1 to 3, then we can just take the two functions so there's my first function, and just subtract them because we're subtracting here. So minus 2 squared, and all of this with respect to x. And so we can combine this into one larger integral to make things a little bit easier on us. Okay, and now this problem can be worked out from here. So if we use our calculator now, then we can turn it on, and then I'm going to go pi times, and I'm going to go to math 9 to set up my integral. And my integral is from 1 to 3, so it's from 1 to 3 of, and then we had x squared plus 4 all squared, so open a parentheses, I'm going to do x squared plus 4, close the parentheses, and all of that needs to be squared. And then minus 2 squared. And I'm taking the integral of all of this with respect to x. Okay, and so that gives me 445.268, and that would be units cubed, right? Whatever units we're using, since we have a volume, it would be cubic units. Okay, before I move on, I want to just kind of generalize the washer method for you, okay? And so the way that's going to work is, you can tell I just have this right here, so I just want to work with all of this, okay? And so this is the integral from, and notice that it's just our, our starting point and our ending point on our integral. So it's going to be the integral from a to b, wherever you're trying to start and wherever you're trying to go to, of, and then this right here is the radius from the larger function, right? So this was the big volume, the red that we had right here. So this big red volume right here minus the smaller blue volume. And so this right here was just the radius of the large function. So I'm going to call it capital R squared, the radius of the large function squared, minus, and this 2 right here, remember, it was the function for blue. For the blue function we drew, it was y equals 2. So that is just the radius of the smaller function squared. The 2 was squared. So I'm just going to call it, capital R for the large function, the radius of the large function squared, minus little r for the radius of the smaller function squared, and then it's just with respect to x, okay? And so this is a generalized form of the washer method. You just need pi times the integral from a to b of your radius, your large radius squared minus your small radius squared, dx.